What if we never had to worry about energy again? No blackouts, no fossil fuels, no nuclear meltdowns, just unlimited clean power beamed down from space 24 hours a day forever. It sounds like science fiction, but 50 years ago, engineers actually tried to build this. They had detailed blueprints, government funding, and absolute confidence it would work. It failed spectacularly. But today, something has changed, and that failure might be about to become our future. Welcome back to the Curiosity Beast. This is part one of our deep dive into solar power satellites, the insane 1970s plan to power Earth from space, and why it collapsed. In part two, we'll explore the modern designs that might finally make it possible. Let's go back to 1973. The United States is in crisis. Oil exports from the Middle East are cut off. Gas prices explode. The price per barrel jumps from $30 to $69 almost overnight. Industries shut down. Muscle cars disappear. Politicians panic. America realizes something terrifying. It's dependent on oil controlled by countries that don't like it. So the government starts funding anything that might break that dependence. Fracking, hydrogen fuel, wind farms, solar panels, and one idea that sounds completely insane, solar power satellites. Here's the concept. You build a massive structure in space, 10 kilometers long, 5 kilometers wide, covered in solar panels. It sits in geostationary orbit, 35,800 kilometers above Earth, always facing the sun. No clouds, no night, no weather. It captures sunlight and converts it into electricity, 8.5 gigawatts. That's as much power as 20 natural gas plants or 8 nuclear reactors. But there's a problem. How do you get that electricity down to Earth? You can't use a cable. So instead, you beam it using microwaves. The satellite uses a 1 kilometer wide antenna made of thousands of radio frequency generators. Together, they create a focused microwave beam that travels 35,800 kilometers to Earth. On the ground, a massive receiver called a rectenna waits, a 10-kilometer wide grid of wires that converts the microwaves back into electricity. After losses, you're left with 5 gigawatts of power, enough to run 5 cities the size of Boston, day and night, no interruptions. On paper, it's perfect, clean, limitless, elegant, except for one tiny issue: building it. The satellite would weigh 50,000 tons, more than the Titanic, and it would have to be built in orbit. The plan called for an army of astronauts working for months in space, welding massive trusses, connecting solar panels, maintaining delicate electronics, all in a vacuum. Every component would be launched from Earth, boosted to geostationary orbit, assembled by hand, and serviced forever. Just keeping it in position would require 93 tons of fuel every year. Drop a comment. Had you ever heard this was a real plan? At the time, it didn't seem impossible. NASA had landed on the moon. The space shuttle was on the way. Everyone believed space was about to become cheap, routine, and accessible. The shuttle was supposed to be a reusable workhorse, flying constantly, slashing launch costs, opening space to industry. But that's not what happened. After Apollo, NASA's budget was slashed. Mars missions were canceled. Moon bases were abandoned, and the space shuttle became a disappointment. Instead of cheap and simple, it turned into a partially reusable monster. It flew fewer than 5 times a year and cost $54,500 per kilogram to launch. Only half of that payload could even reach geostationary orbit, so the real cost doubled, over $100,000 per kilogram. Launching a 50,000-ton solar power satellite would cost more than $5 trillion. That's just for launches, not construction, not maintenance, not ground infrastructure. It was impossible, completely insane. But that's not what finally killed the project. Oil did. By 1980, the oil crisis ended. OPEC increased production. Prices collapsed to $34 a barrel. Suddenly, nobody cared about alternative energy anymore. Funding vanished. Engineers moved on. And the dream died. For 40 years, solar power satellites became a cautionary tale, proof that some ideas were just too big, too expensive, too early. Then something changed. SpaceX. Falcon 9 dropped launch costs below $3,000 per kilogram, nearly 20 times cheaper than the shuttle. And if Starship succeeds, costs could fall below $200 per kilogram. Solar panels are now lighter, more efficient, easier to deploy. So the question returns, could it work this time? That's what we'll explore in part 2. Modern engineers have redesigned everything. Satellites that weigh 40 times less, robots instead of astronauts, new transmission methods, microwaves, lasers, even giant orbital mirrors that reflect sunlight to Earth at night. If you want to see what the future of space-based energy really looks like, make sure you're subscribed. Part 2 is coming next, and trust me, the new designs are wild. Thanks for watching, stay curious, and I'll see you in Part 2.